So now that we showed that using reductions won't quite work here, let's go ahead and try to introduce a new algorithm to approach the shortest path problem when we have these weights. The algorithm we're going to introduce is called Dijkstra's algorithm. So let's start by talking a little bit about its inventor, Edgar Dijkstra. Now, before I kind of share some things about him, I do want to mention some, at least from personal context for me, I think it's generally pretty toxic the way that we talk about kind of these like founding figures or historical figures in any field in particular. I think there's a lot of glorification that goes on with people from the past, which is kind of disingenuous from the perspective of, when they were doing this, they weren't knowing that they were creating this thing that ended up being really important. And so sometimes we wrongly compare ourselves to these people. And I think it's kind of ignores some of the exclusion that happened back then during Dijkstra's time, the people that were excluded from having a voice in that field. So I usually not a fan of talking about all these great people from the past. However, Dijkstra does have a lot of really great things, and I do want to highlight that he has accomplishments and did shape the field of computer science in a way that I really resonate with. For example, he kind of has this nice philosophy of what computer science is, or he thought it was, that I think really quite captures what I think of the field as, which is the quote that is commonly quoted from him is, "Computer science is no more about computers than astronomy is about telescopes." And his work really focused on the aspect of computation being separate from the idea of a computer and more abstract than that, more universal. So really his vision of computer science was about computation rather than computing, which doesn't sound like a very clear difference, but actually has a lot of big impacts on how we teach things like computer science. So for example, you've noticed in 373 that at least in the lectures, we don't talk a lot about programming. We talk about abstract ideas that apply to any computing scenario, but you happen to implement in Java. This idea of what computer science is so much broader than programming. I do really like this perspective from Dijkstra. Now, he also ended up creating a lot of very popular algorithms, one called Dijkstra's algorithm that we're going to talk about right now. Now, enough about people from the past. Let's talk a little bit about what this algorithm is, why it's useful. I'm going to mention before we start that this algorithm is going to be a little reminiscent of BFS, but updated to handle weights. Now, one thing that's a bit weird is I think a total normal reaction to seeing what the algorithm I'm about to introduce is probably scratching your head a few times. Be like, I don't understand what this does or how it works or why it works. That is totally normal. Dijkstra's algorithm is very weird the first time you see it. This is probably the one video I totally think the majority of the class will have to rewatch and pause in the middle. It is a weird algorithm the first time. And the way I'm going to present it is unfortunately a little weird. I'm going to start by explaining the kind of like big idea, then explain the pseudocode, kind of what is it trying to do at each step, and then go through an example. And so it will be kind of awfully abstract the first time that you see this, but I think it will clear it up a lot with an example. But again, don't worry if you feel like you need to go back and watch it again. I wish when I was taking my data structures course, Panopto was not that popular. So I kind of had one shot to see this in lecture. So you have a huge advantage here over me of being able to go back and rewatch this. So what's the big idea of Dijkstra's algorithm? It's going to be a lot like BFS, where you have a set like your perimeter, but we're going to talk about the set that we call the known set. It's the set of nodes that we know the shortest distance to. Now, one thing that's important to mention is this diagram I'm about to show you, and we're going to use quite a lot, has a lot of information packed into it. I'll get there in 1 second. But the idea of Dijkstra's algorithm is we have a set of nodes that we know the shortest distance to. And outside of that set, we have a perimeter of some sort of the nodes that we think we have a good idea of what the shortest distance to, but we aren't quite certain yet. And then outside that perimeter is nodes we haven't even considered yet. Where they're outside of our field of vision. We'll get there to those later. how Dijkstra's works is we start all nodes as having distance infinity away from our starting vertex. So we're going to start by assuming every node is infinitely far away, and we're going to label our starting node as having distance 0 away from itself. Now, what is this diagram trying to show you? Well, it's a picture of a graph, and on that graph, each edge has a weight shown as a black number. So that's showing what's the edge weight by taking this path. In the known set, there are also some red numbers on top of the nodes. These are showing what we know is the best or the shortest distance to that node. So the shortest distance to C is 1. And because we're going to kind of make an invariant in our algorithm, that putting things in our known sets means we know the shortest distance to that node. Now, in our perimeter and outside of that, things are a little less clear. So we mark, for example, the nodes in the perimeter. We think the shortest distance is 4, and so we mark it with some question marks. We're not quite certain yet. So we'll make a decision once we add it to our known set, but we're not quite sure. And then we also set infinity to all the nodes we haven't even looked at yet at all. And so the kind of way the algorithm goes at a high level is we're going to pick the closest node that's currently in our perimeter, add it to our cloud or our set of known vertices, and then update all of its neighbors saying, we now know the shortest distance to this node. Let's update all of its neighbors to see if there is a better path through this node that we just added. Kind of weird, kind of abstract. Now it's going to get even weirder and abstracter as I show you some pseudocode. So here is Dijkstra's pseudocode at a high level. And again, this slide is going to have a lot of information. It's going to look really weird at first, and we're going to walk through examples soon. So we start by initializing some data structures to keep track of information, just like BFS for the unweighted shortest path problems. So we're going to have a set of known nodes, which is going to be very similar to our visited set. And we're going to have that map edge 2 to keep track of which edge we came from to any particular node, and that dist2 map to keep track of the distance. We start by initializing that dist2 map to have all nodes with distance infinity, except our starting node, which we're going to set to 0. The key idea for Dijkstra's algorithm is that we're kind of updating what we think is the best distance so far, and that dist2 map is going to store that. If we ever find a shorter path, we'll update dist2 and edge2 accordingly to say, hey, we found a shorter path to this node. Let's not add it to our known set quite yet. And then so how Dijkstra's work is it's kind of a bunch of iterations. While there are vertices that are not in our known set, grab the closest one. So grab the vertex in that perimeter that's the closest as the shortest distance. And now we're going to state we now know its distance. Add it to our known set. And then, and importantly, order matters here. We always are going to visit the closest node first. So whenever you pull something from the perimeter, it has to be the node that has the shortest distance in that perimeter. That's going to play a key role in this algorithm. Now what we're going to do is now that we've added a new node to our known set, we might need to update its neighbors. So I've just popped up here on the top. I'm going to hide my webcam for a second. I've shown a little picture of a graph. Now what this picture is showing is that we had this graph with nodes A and B in our known set already. On this iteration of Dijkstra's algorithm, we just added C to our known set. That was the node that we just pulled off that used to be in our perimeter. Our perimeter now currently has D in it. We just moved C from the perimeter to D. Now we want to figure out, now that I know the shortest distance to C, and I'm assuming, and one of the things that we need to make sure is true, is whenever we add a node to our known set, this is the new shortest distance, or that's the correct shortest distance to that node. But now that I know the shortest distance to C, I wonder if there's a better path to D. So currently what we thought of, because D was in our perimeter, we had an idea that the shortest path was from A to B to D with a cost of 7. But now, since I just added C to my known set, and there's that had distance 3, And because there's an edge of with weight 1 between C and D, I know that there's a better shorter path from A to C to D that has cost 4. And so Dijkstra's algorithm will update any nodes that have a better distance from this node you just added to the known set. So all of this kind of pseudocode down here is considering all of the nodes that were reachable from me, the node that I just added to my known set, is going to all of those reachable nodes through me better than the path that we currently had as what we thought is the best path. So if the distance through me, my distance plus W, the weight of this edge to that neighbor, if that's less than what I currently thought was the best, then update all of my state. Okay, one last abstract thing before we get to an example. So here is kind of the key properties that we're going to assume are true through our run of Dijkstra's. And when you think about key properties that you assume are true, you should be thinking of the word invariants. These are the invariants we rely on in our algorithm that we're going to maintain so that this works. So the first invariant is once a vertex is marked as known, we now know its shortest path. So that's kind of our invariant, is whenever we are at the point of adding something to our known set, there is no way that there's a shorter path somewhere else. Now, one of the things that's useful about this is we can always reconstruct the path by following those back pointers, that edge to map. So we can always figure out for any node in our known set how we got there. Then our kind of other invariant is kind of the converse of this. Any node that is not in our known set, we don't know. There might be a shorter path that we haven't discovered yet. So we are not going to make any claims that we know the shortest path yet. However, we do know, in some sense, an upper bound on the shortest path, right? In that example before, when I knew that there was a path to D through B, I knew at most the distance to D was 7. There might have been an even shorter path, which I haven't found yet. That's okay. But I kind of know this upper bound. That's kind of one of those ideas. Now, whenever you update the path to a node in Dijkstra's algorithm, they call this a relaxation. It's a term that doesn't have a really great definition or meaning. You just probably will see that term relaxation or relaxing a lot, so I thought I should mention it. When I was prepping for this lecture, I was like, I've heard this term relaxing a lot, but I don't actually know where it came from. I looked it up, and there's no conclusive answer. The one I found was it comes from the idea of the algorithm kind of updating these shortest paths. So previously, you might have thought the shortest path to get from A to D was 20 miles, and then you found out that it was only 3 miles. And wow, how relaxing it would be to know that you don't have to walk those extra whatever miles. I forgot the numbers I used already. So we'll commonly call this relaxations or relaxings, but the reason why it's called that is not important. Our third and last property that's really important is the way we process our nodes in that perimeter is always finding the vertices that are closer. So we're going through the closest vertices first. Let us confidently say that we will not find a shorter path later, because it's not possible to find a shorter path that uses a farther vertex that we haven't considered yet. That's very confusing. That'll make a little bit more sense later. So how are we actually going to do this? What does this algorithm look like? I finally am going to get to an example, which will hopefully make things make a little bit more sense. So on the top left up here, I'm going to turn my webcam back on so I can gesture with my hands. The top left up here, I have a picture of a graph. I've already gone ahead and initialized all of the weights from Dijkstra's algorithm. So all of the distances to nodes I've set to infinity, except the node A, which is their starting node, which we're going to say is distance 0 from itself. In the bottom right down here, I have a table. And what this table is doing is it's keeping track of the state of all of those data structures we initialized at the beginning. The known set, the distance to map, and the edge to map. And you don't need to necessarily think about them as one big table, but it's kind of useful in terms of trying to do this by hand to have everything in one place. We also are going to keep track of what we call the order added to the known set. which is keeping track of when we've added things to the known set. This is not something that's strictly necessary from Dijkstra's algorithm, but we're going to find is useful in keeping track of, when doing this by hand, what has happened and when. So we set up all the state. Now we need to run Dijkstra's algorithm. And Dijkstra's algorithm runs in a series of iterations. And we start with the first iteration that's going to end up adding kind of the closest node here. Oh, is that going to go? Oh, there we go. We're going to add our closest node, our starting node, to our known set. So what we've done now is we've marked it as known. It's in our node set. So we've added it kind of as the first entry in our known set. We've updated its distance in this case and the edge too. In this case, these are a bit weird because it's just the starting node, so there's nothing special there. But now that second step is to go update all of its neighbors. So for each of its neighbors, we're going to update its path to get there if taking this node we just added to our known set, results in a shorter path. Now for all of B, C, and D, their original distance 2s were infinity. So taking a path through A is definitely better. So we're going to say B is going to be at most 2. Why? Well, because the distance to get to A is 0. And then the distance on that edge weight, A to B, is 2. So we're going to suppose that the current best distance to B is 2. And this is a proposal. This is not saying definitively, oh, I know the best distance yet. This is just saying, this is what I think it is right now with what I have in my known set. Similarly, C will become 1, and D will become 4. We also keep track of edge 2. Which edge did we take to get to this node on this potential shortest path? Now that we've updated everything, we've now finished the first iteration of Dijkstra's algorithm. We can now move on to the second one. The second iteration says, grab the node that we currently know the distance, our proposal distance to, that has the smallest distance to. In this case, that's going to end up being C, because C has a proposed distance of 1. That's the smallest proposed distance we've seen. So we are going to add C to our known set. We are going to solidify its distance to 1, and then go update all of its neighbors. Well, C has a couple neighbors. The first one's A. Well, because A is already in our known set, there's no need to try to update that again. Particularly, you could see from this example that the path from A to C to back to A has cost 10, which is definitely bigger than the cost of 0. That's why we're not going to consider nodes that we already have added to our known set. There's always going to be longer paths. Now, if we consider the other neighbors, C has a neighbor from C to E with edge weight 11, we're going to now associate the distance 12 to E. Why 12? Well, the edge weight here from C to E is 11, and the cost to get to C, the distance to C, is 1. 1 plus 11 is 12. But again, we're not saying definitively that the distance to E is 12. We're just saying our proposed shortest distance to E is 12. But we'll solidify that later when we add it to our known set. Now we finish the second iteration of Dijkstra's algorithm. Now we continue. The next node in our distance 2 that is not known, that has the shortest distance to, is B. So we add B to our known set and update all of its neighbors. We update F to have distance 4 because the distance to B is 2, and the edge weight from B to F is 2. We update F to be 4, and we say we came there through B. Now, B has another out neighbor, C, but we already have that in our known set, so we're not going to touch that at all. And again, you could see that that's actually a larger edge weight, a larger path than what we already had, so it's not going to be even useful anyways. But then there's one extra neighbor from B to E. The cost to get to B was 2. The cost to get from B to E is 10 for a total cost of 12. That currently matches what we thought the best path to E was from A to C to E. Now, there's a kind of just choice you have to make about how you handle ties. In our example, we're going to say that you only update a shortest path if it is strictly shorter than. If it's equal to, you just keep whatever was there originally. But you can kind of decide what do you want that tie breaking logic to be. So We've now updated all of our neighbors. And so now we continue to the next iteration of the algorithm. So we're going to add D to our node set because out of the 3 nodes in our parameter, D, E, and F, D seems to have the shortest. Again, another tie case here because both have path 4 or distance 4. And again, it shouldn't matter how you handle ties as long as it's consistent. And if on project 4, when we ask you to implement Dijkstras, we will tell you how to break ties. So we add D to our known set, update any of its neighbors. It has no neighbors that are not known, so that's kind of a no-op. Now we update our next one, which is F. It has a neighbor H, and the cost to H will be 4, the cost to get to F, plus 3, the cost to get from F to H. Notice this updating distances is actually a constant time operation because we're storing the distance to a node in a map. We can just find, oh, this is the distance to F, and then we just add on, well, what's the distance that was in this edge to get to H? So updating distances and these edge 2s is a constant time operation, which is pretty nice. Okay, now we keep continuing. We add H to our known set because that was the closest node. We now update G to have potential distance 8. Now 8 is the node that gets added to the known set on the next iteration of Dijkstra's algorithm. And now we update all of its neighbors. Well, the only neighbor of it that is not known is E. Well, what's the cost to get from G to E? Well, that's 3. And what's the cost to get to G? That's 8. That's 11. And 11 beat our current proposed shortest path of 12. So we update E to have a distance 2 of 11 and an edge to G. This is precisely why we process nodes closest. We always pick the one that has the shortest distance to. That prevents us, even though we added E to our parameter early on, we never went and added it to our known set until we knew there was no shorter path. And in this case, there was a shorter path that happened later, but because we didn't process it earlier, we are totally fine. And then we add E to our known set. So kind of weird, very strange algorithm. Now, I can't quite convince you right now why this works. That's the target of my next video. My next video is going to explain why does this algorithm work in the first place. The last thing I want to mention in this video, because this video is getting a little long, is how do you interpret the results? So once you've run Dijkstra's algorithm, how do you actually take this table that you've just built up to interpret the results? Well, this table tells you what's the shortest distance to any given node from our starting point A. So you could just figure out, oh, what's the shortest distance to F? Oh, that's 4, because that's what the table says for the row F. And just like with unweighted shortest paths with BFS, you can reconstruct the edge 2 pointers to figure out what's the path to get there. You can use these back pointers to kind of go back to where you were before. Dijkstra's also forms a shortest path tree. So everything we just talked about, unweighted shortest paths back on Wednesday, applies here. You have this answer that tells you how to get to any node and what's the distance there. It's just different now because the algorithm that we ran respected those edge weights. That's all I want to mention in this video. In our next video, we're going to talk about why this works. I recommend watching that one first before maybe coming back and trying to watch this again and see kind of how this algorithm went through till the end.